Hey guys, so we're going to talk about Boyle's law today. So it's the effect of changing size of container. I feel like there's a few words missing there. Okay, so what if temperature and moles do not change and we just look at the relationship between pressure and volume? Our equation would look like this. P1 V1 equals P2 V2, and this is going to be Boyle's law, which states that at a constant temperature, the volume of a gas is inversely proportional to the pressure exerted by that gas. Okay, which means that an inverse relationship, if we were taking a look at pressure and volume, if pressure goes up, then that means volume is going to go down. And if volume goes up, pressure is going to go down. Okay, so think of two kids, Paul pressure, Victor volume on a seesaw. If Paul goes up, Victor goes down. If Victor goes up, Paul goes down. This is an inverse relationship. Okay, so really quick, let's go ahead and take a look at this here. This is a simulation to kind of show you the relationship between all our variables. Okay, so if temperature was held constant, okay, this is a piston right here, the stuff that makes your engines go in your car. Okay, so if we decrease the volume of our piston, okay, we can see that the pressure increases when volume decreases. Remember, what causes pressure is the collision of those gas particles inside our container. Okay, well, if they don't have that much room, okay, there's going to be a lot more collisions versus to where we have a larger volume, they have a lot more space, the less chances that they'll collide with each other. Okay, so it definitely has to deal with how much space they have between each other. Okay, so let's go back to our PowerPoint. Okay, so if we take a look at our examples, okay, so if gas is compressed from 2 liters to 1 liter, then the pressure will blank by a factor of 2. Okay, so if we're taking a look at volume, okay, we are making the volume smaller. So we're decreasing volume. So what would happen to pressure? Remember, it's an inverse relationship. So if volume is decreasing, we would expect pressure to increase. Okay, and if gas is expanded from 1 liter to 3 liters, so that means our volume is increasing, we would expect our pressure to decrease. They would have a lot more room. Your gas particles have a lot more room to move around, so again, the less collisions there will be. So our pressure is going to decrease. Okay, and then gases cool when they expand and heat when they compress. Again, this has to do with the collisions of gas particles, the kinetic energy. Okay, it goes back to that kinetic molecular theory. Okay, so when you compress them, there's going to be more movement of those gas particles. The more movement we have, theoretically, the higher the temperature will be. Okay, and then the less, the more volume they have, then the more space they have, the cooler they should be, the less movement there should be. Okay, so if the volume of a container decreases in size, the pressure of gas particles in the container increases. Okay, and then I believe some of you guys who are following along in your notes, okay, you have a question as what will happen to you in space. Okay, if you forget to wear your suit in space, you will explode. Okay, and the reason being is if we're here on Earth, we are surrounded by the atmosphere. We have atmospheric pressure. Okay, but the second we take a step outside of our atmosphere, there is no pressure. Okay, so if there is no pressure, then that means that the gas will just be free to go everywhere. There's nothing containing the pressure of the gas molecules in our body. So that is why we would explode. Okay, so this brings us to our sample or example problems. Okay, and again, our formula for Boyle's law is P1 V1 equals P2 V2. So the pressure of a 3.5 liter balloon was determined to be 1.5 atmospheres. Assuming that the temperature remained constant, what would be the volume of the balloon if the pressure was decreased to 0.45 atmospheres? Okay, so if we're taking a look at what we've been given and what we're trying to find, they give us an initial volume, an initial pressure. Okay, and then they ask us what would be the volume of the balloon if the pressure was changed to 0.45 atmospheres. So that's going to be our P2. So if we plug in our variables into our formula up here, okay, we would get something that looks like this: 1.5, which is our P1, 3.5 liters equals 0.45 atmospheres times our unknown V2. And so simple algebra, we're going to multiply these two values and then we're going to divide by 0.45. And you should get an answer of 11.667. But of course, rounding to the correct number of significant figures, we would get a final answer of 12. Okay, now if you want to go ahead and do number 2 on your own, please go ahead and pause at this time. Okay, but if not, let's go ahead and keep going. So number 2, at 45 degrees Celsius, a certain container of gas has the volume of 580 milliliters and a pressure of 980 millimeters of mercury. What would be the new volume of the gas at 250 millimeters of mercury and 45 degrees Celsius? Okay, so again, let's take a look at what we've been given and what our unknown is. So if you notice, they do give us temperature. Okay, they give us 45 degrees Celsius and then again 45 degrees Celsius. But I will tell you this now. A lot of the gas laws that we're going to be looking at have an initial temperature, final temperature, initial pressure, initial volume. We're looking at variables that change. So for the fact that 45 degrees temperature or our temperature doesn't change, that means it's just extra information. We don't need this. It stayed constant, so we can actually ignore it. So really the only variables that we're looking at would be our volume, our initial volume of 580 milliliters, and our initial pressure of 980 millimeters of mercury. So our unknown would be our V2, our final volume, and then our final pressure is 250 millimeters of mercury. So plug those into your equation or your formula, and you should get 980 millimeters of mercury times 0.580 liters. Okay, just to keep things simple, it's always easier just to use liters, not unless your question asks you for millimeters, then you can go ahead and leave it in milliliters, okay? But it's always easier just to use liters. Okay, and we set that equal to 250 millimeters of mercury times our unknown. And again, to solve, we would multiply these two variables, and then we're going to divide by 250, and we get 2.2736. But of course, we need the correct number of significant figures. So if you leave it in liters, we would get 2.3 liters. Or if you convert back to millimeters, we would just simply multiply that by 1,000, and we'll get 2,300 milliliters. Okay, and that is it for Boyle's Law. If you guys have any questions, please feel free to comment or ask me in class.